Just give me a moment. I think I have to just minimize this thing. So today, yes. So today we will start the advanced regression techniques beyond OLS, means GLM and logistic regression. So the today's session objective is to understand why simple linear regression often fails in complex agricultural, biological, and any other fields data, and to learn GLM for non-normal data, limitation of OLS, concept of GLM, and concept of logistic regression, and a little hands-on implementation of logistic regression using R that you have already seen in your last session. So simple linear regression, very basic regression technique when there exists a linear relationship between two variables. That means a approximate linear relationship. That means we can't say the exact linear relationship exists between the two variables. So all times we are saying that there exists approximate relationship, and that's why we are writing the equation with the error terms, because we can say our x and y are approximately linearly related. Now if we want to put the equal sign in their relation, that means y equals to mx plus c, that is basically straight line equation. So in that case we have to add the error term to remove the approximate thing. So today's motivation is why move beyond ordinary least square, why it is necessary to learn the GLM, because nature of the nonlinear relationship. Suppose there exists a nonlinear relationship, suppose S-type relationship exists between the two variables. So that kind of relationship actually arise in biological growth data that rarely follows the perfect straight line. And another thing is curse of dimensionality. If there are a huge number of features that exist in the data, and the number of features are more than the number of observation, in that case we are saying that this is a big data and there are huge number of features. So this actually the curse of known as the curse of dimensionality, because due to huge number of features your model complexity will increase. Another one thing is multicollinearity. Multicollinearity is if there exists a strong correlation exists between the explanatory variables, and this situation actually known as the multicollinearity situation. If there exists multicollinearity in your model, so your model performance will drastically reduce, because your model did not distinguish, your model could not distinguish the class levels, various class levels. So that's why multicollinearity is a very important factor for generalized linear model. Quick recap of linear regression, that you all know the linear regression model actually looks like a straight line equation that I have already told you. Suppose x1, x2, dot xk, suppose we have k explanatory variables and y is our dependent variable, and we assume that they have the approximate linear relationship between the dependent and the independent variables, and we have collect n observation on this k measurement. So we have the data matrix based on the n observation and the k features, and that data matrix will be of n cross k data matrix. So now if we build a linear regression model, your model looks like this equation. But before building the linear regression model, we have to make some assumption on the model error. That is model error and about the model. This is response variable and explanatory variable should be approximately linearly related. Errors should be normally distributed. That means if error is normally distributed, then your dependent variable should also have to normally distribute it. That means you can only when if your response variable is normally distributed, then only you can build the linear regression model. Another assumption is that error should be independently and identically distributed. That means your model error not be autocorrelated. If the errors are autocorrelated among themselves, then you cannot use the method of OLS estimation to estimate the parameters of the linear regression model. So in that case, your variance of the model will drastically increases and your model performance will drastically decreases. Another thing is explanatory variables are non-stochastic. In every linear model, that is linear regression model, GLM, we are assuming that our explanatory variables are non-stochastic. Non-stochastic means we will not assume any distribution about the explanatory variables. So these are the four assumptions of linear regression model. So we have to check after building the linear regression model whether our error is normally distributed, whether our errors are homoscedastic. That means all the variance of the errors are same or not. And another thing is that whether errors are autocorrelated or not. If any of these assumptions are violated, then we have to adopt some transformation techniques that actually exist in our literature, like Box-Cox transformation, Box-Cox Tidwell transformation, and there are so many transformations that exist. So before proceeding to model any relation that will be linear, so at first we have to check whether our response variables distribution is normal or not. If normal, then we can build the linear regression model. Otherwise, we have to adopt some other methods that actually known as generalized linear model. And the concept of generalized linear model actually given by McCullough and Pitts. They are professors of Stanford University. So they have provided the technique to model if your response variable is not normally distributed. Suppose apart from normal distribution, your response variable follow like Weibull distribution, log normal distribution, gamma distribution. So in that case, we have to find another method to link the relation between the response variable and the explanatory variables. Okay, let's go to the next slide. Limitation of OLS. So here we will discuss the limitation of OLS. Why OLS is very weak if our distribution are not normally distributed. So first point is sensitivity to outliers. OLS basically works by minimizing the sum of square of the distance between the points and the best fit line. So that's why, because the errors are squared and a single extreme outlier can be disproportionately pull the regression towards the itself. Because if suppose if there exist any outliers in the data, then your regression line just pull towards that point. Another thing is assumption of normality that I have told you. In linear regression model is very rigid, that if only linear regression model only build on the condition of normal distribution of the response variable. But if your response variable could not follow normal distribution, rather it follows other non-normal distribution, in that case your linear regression model will fail. Second thing is multicollinearity. When variables means explanatory variables are intercorrelated among themselves, then OLS cannot distinguish the individual effect of each explanatory variables. Another thing is overfitting. OLS has no built-in mechanism to punish complexity. That means linear regression actually shows the better result in training dataset, but it shows very poor result on the testing dataset. That's why linear regression has the demerit of overfitting issue, because linear regression is very sensitive to the overfitting issue. So that's why linear regression is very poor model. As it is good as a base model, but for complex data it is very poor model. Lack of feature selection, it cannot automatically set the coefficient to 0. Another thing is homoscedasticity. In reality, variance often changes. So for example, the variance in crop yield might much higher at high fertilizer levels than at low fertilizer. Second thing is requirement for n greater than p. That is the big data concept. If in modern data genetics, we have thousands of gene markers, but only a few hundred plant samples. Suppose for a cancer disease, suppose in our body we have 30,000 genes, but for a cancer disease, suppose skin cancer disease, only 10,000 genes are responsible. So rest of the 20,000 genes are not usable for our model compilation. So that's why so we have to discard this variable based on the mathematical concept. So this thing actually give the concept of lasso regression and ridge regression. Lasso basically give the concept of sparse models. Sparse models means we have to reduce the model to a significant model after discarding all the unusual variables from the data. So how do you do that? There are another advanced techniques known as lasso, ridge, elastic net, and other things. Next, we will uh, introduce the today's topic, the generalized linear model. Generalized linear model are those regression models which consist of two components, and one is random component and another one is systematic component. Random component is the component of the model. This is basically the dependent variable component, where we are assuming that our distribution of the random variable coming from a non-normal distribution, non-normal family, but it should belong to the exponential family of distributions, like gamma distribution, between gamma distribution, and exponential distribution, and log normal distribution, etc. are all belongs to the exponential family of distribution. So if it is coming from the exponential family of distribution, like binomial, Poisson, then we can build a generalized linear model. And another one is systematic component. Systematic component basically form of the relation between systematic component actually the form of the relation between the explanatory variable to the mean response of the variable. Oh, another thing is linear regression model, we are basically trying to model the conditional average of the conditional average with the predictors. Same thing we are doing in the GLM. Okay, so we all know about the conditional expectation. So basically, regression model is nothing but the conditional expectation. Conditional expectation means expectation of y given x equals to x and so on, beta naught plus beta 1 x. So in place of where here the linear regression, here yi equal to beta naught plus beta 1 x1 I and so on. So here I is nothing but the conditional expectation. That means expectation of yi given x equals to x1 and x equal. That means in linear regression, we are trying to model the conditional average. Now, if distribution of y follow, suppose Bernoulli distribution, okay, suppose y follows Bernoulli distribution, like now I will try to show you by hand explain. Suppose okay, just wait. Just wait. In linear regression, we are doing y equals to x vector, that's equal to x vector is beta naught plus beta 1 x1 plus beta 2 x2 and this thing. So if our y follows Bernoulli P instead of normal distribution, in that case our distribution is probability of y equals to 1 is p and probability of y equals to sorry guys. Mm, mm. In case of linear regression, what we are doing? We are doing that expectation of y given x1 equals to x1, comma x2 equals to x2, comma x3 equals to x3. This is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. So this is our actually regression model. That means our actually y given x1 equals to x1, comma x2 equals to x2, comma x3 equals to x3 actually follows normal distribution with mean beta naught plus summation beta I xi and comma sigma square I. So this thing actually for it, actually the case of linear regression. But instead of this, if your y follows Bernoulli distribution, then what happened? That means your response variable is like takes only 0 and 1. That means yes and no type. So in that case, your expectation of y is equals to your p, because your distribution, your PMF is nothing but p to the power y into 1 minus p whole to the power 1 minus y. That means probability of y equals to 1 is your p, and probability y equals to 0, this is your 1 minus p. That means your q. So in that case, you are basically modeling probability of y equals to 1, that equals to beta naught beta 1 x1 plus beta 2 x2 plus beta 3 x3. So instead, in linear regression model, we are basically try to model the distribution, try to model the conditional average. In case of GLM, if your response variable follows Bernoulli distribution, we are trying to model the probability of getting yes. That is the main difference between linear regression model and the generalized linear model. In generalized linear model, if your response variable, suppose your response variable follows the count of the data, so in that case, that means if your response variable follows Poisson distribution, in that case you have to use the generalized linear model. Suppose we are taking here y is your Bernoulli distribution. In that case, we are trying to model the probability of getting 1, that means probability of getting yes with respect to, that means how the explanatory variables affect the probability of getting yes. So if we trying to model this scenario, then we have to use the none other than logistic regression. So now the logistic regression, Poisson regression, and log normal regression, gamma regression, there are various types of regression based on the based on the link function. Link function is, what is link function? One thing you note that expectation of y given x is your beta naught plus beta 1 x1 and so on. Now one thing, your average can be greater than 1, so probability cannot be greater than 1. So that's why we have to introduce a function which will take the whole average as an input and give us the output between 0 and 1, and this function actually known as the link function. Link function is just convert your average into the probability function, probability value. So this function is known as, if your link function is your logic function is known denoted by 1 by 1 plus e to the power minus eta. Eta is your expectation. So in that case, you will obtain the logistic regression. That is our today's topic, the logistic regression. Okay. So this is our logistic regression. Binary logistic regression means if your, that's I have told, if your response variable follows the Bernoulli distribution, that means you want to model the binary outcomes. That means yes or no. So this thing actually modeled as log of odds. This p by 1 minus p is known as the odd ratio or the odds. So that we are trying to model the log of odds as beta naught plus beta 1 x1 plus beta 2 x2 and so on. Here p is the probability of success, and this model links the predictors to log odds of the outcome and is widely used to estimate the association and predict the probabilities for binary data. So this is the all about logistic regression. Now we will try to understand what is the odds and odds ratio. Odds are the odds of an event are the ratio of how likely the event is to occur and how likely it is not to occur. Suppose p here, if p tells us how likely an event to occur, then 1 minus p all tells us how likely it is not to occur. And the odds are the ratio of these two components. Suppose, for example, suppose we have an event and the occurring of the event with probability 75%, then odds of the event are 3:1. So what is the odd ratio? An odd ratio actually compares the odds of an event between the two different groups. For example, suppose the probability of a disease is 0.35 for a man and 0.25 for women. Then the odd ratio is 1.62. Now, if the odd ratio value is greater than 1, that means 62% chance, that 62% more risk of getting the disease for men. This is the interpretation of odd ratio. Suppose if odd ratio is greater than 1 or less than 1, implies positive or negative association between the continuous predictor and the outcome. Suppose if your odd ratio is greater than 1, like odd ratio is 1.62, that implies that men has 62% greater odds of greater odds of the risk to disease than a second group, or the 1.45 times the odds of the second group. And that's opposite interpretation for the odd ratio less than 1, which is 100%. Formula is 100% into 1 minus odd ratio, and this represents the percentage of lower odds. So odd ratio equals to 0.81, which is less than 1, and this implies that first group has 19% lower odds of the outcome than the second group. Interpretation of the regression parameters. Here is the same interpretation as of the linear regression. The intercept is the log odds of the outcome when all the predictors are at 0 or their reference level. So here we use the exponential function, that means e to the power beta naught, to convert the intercept to odds and the inverse logic function. This is the actually logic function, and the shape of the logic curve is like S. So for a continuous predictor, the regression coefficient is the log of the odds ratio comparing individuals who differ in that predictor by 1 unit, holding the other predictor fixed. That means if you fixed all the predictors, suppose we want to check suppose our model is limit nature p by 1 minus p, beta naught plus beta 1 x1 plus beta 2 x2. Now if you fix the x2, that means x2 equals to 0, then you will get, if you increase the 1 unit in the x1, then your log of odds actually increase by beta 1 times. That means odds at the probability of increasing the probability of getting the disease with e to the power beta naught plus beta 1 times. So for a categorical predictor, each regression coefficient is the log of the odds ratio comparing the individuals at given level of predictor to those at reference level holding the other predictor fixed. And to compute odd ratio for xk, exponentiate the corresponding regression coefficient e to the power beta k. Thus, that means if you want to find the odds, then you have odd ratio, just you have to exponentiate the estimate value of the parameter. So we have a data analysis example. We have simulate experimental field trial data whose sample size is 150, and objective is to predict the disease outbreak based on the environmental and soil factors. So our variables are, target variable is disease, whether disease is present or not. If disease is present, then we have encoded with 1. If disease is not present, we have encoded with 0. And other explanatory variables are temperature, humidity, and temperature measured in degree centigrade, humidity in percentage, rainfall, nitrogen kilogram per hectare, and soil pH, that is range from 0 to 14. So this is the actual, this is the model summary of the data. Here you can see this is the model estimate of the parameter. That means if you change, if you fixed your humidity, nitrogen, and soil pH, then if you increase the 1 unit temperature, then your log odds will increase by 0.1574 times. So that means if you see the odd ratio, that is 1.17, that means your in temperature each unit, if you increase the each unit in temperature, that increase the odds of disease by 17%. That means the risk actually increase by 17%, since the confidence interval does not include 1, and this effect is statistically significant. Similarly, for humidity, you can see that 0.045 times actually increase. If you increase 1 unit in if humidity increase by 1 unit, then log of odds actually increase by, here is log of odds increase by 4.6%. So this the odds of disease increase by 4.6%, because your odd ratio is 1.05. That means 1 minus 1.05 minus 1 into 100%. So this effect actually is statistically significant, because all the p values corresponding to temperature and humidity is less than 0.05, because we have tested at 5% level of significance. For nitrogen and soil pH, you can see the probability value, actually the p value is greater than 0.05. That means it has nitrogen and soil pH has no significant effect on the disease outcome. Second thing, like key takeaways is temperature and humidity are significant positive predictors of disease, while nitrogen and soil pH do not show statistically significant effects in the model. So this is all about the concept of logistic regression, how logistic regression comes from GLM, and why GLM is necessary to analyze the real life complex data that I have discussed here. So this is all about the advanced. There are so many advanced regression techniques, like there are lasso regression, ridge regression, and in the philosophy of GLM, there are lasso for GLM, ridge for GLM, and sparse modeling of the data, and project pursuit regression, elastic net, Bayesian shrinkage. There are various types of statistical models to analyze the complex biological data like genetic data. So this is the small part of the advanced regression technique. This is that's all. Thank you for your attention. Now, if you have any queries or question, you can tell me.
Thank you so much, sir, for the
Hmm.
lovely presentation and informative presentation. So now I request the participants that if you have any query, you can unmute yourself and ask.